Good day, everyone, and welcome. I'm Jack Van Horn from the University of Virginia, and I'm very proud to welcome you to this edition of our 2023-2024 Foundations of Biomedical Data Science seminar series. This lecture series is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA College of Arts and Sciences, the UVA School of Data Science, and through a grant from the National Institutes of General Medical Sciences. Since 2016, the Foundations of Biomedical Data Science seminar series has focused on the use of data science methodologies, artificial intelligence, deep learning, and statistical modeling as they pertain to different themes in the biomedical and health sciences. Our selected theme for this year is focused on building partnerships for generative AI training in biomedical and clinical research, where every Friday we enjoy presentations from a wide range of leading thinkers about the issues, promise, and opportunities associated with the emerging notion of AI-based methods in biomedicine. Indeed, we'd like to remind everybody that our 2023-2024 application cycle is open, and we strongly encourage junior faculty members working in areas such as the development of generative AI methods applied to biomedical research, as well as those junior faculty actively utilizing AI in their biomedical teaching and research to consider applying. We find that this is a very exciting and engaging program, bringing together AI platform developers and university level educators to better understand the power, the promise, and potential perils associated with generative AI. Participants selected for our Biomedical Data Science Innovation Lab program will leverage these seminar presentations as vital material for our culminating in-person manuscript and grant project development workshop to be held at the Bahia Beachfront Resort located in sunny San Diego, California in June of 2024. Today, I am delighted to welcome our speaker, Anna Baglione from Stanson Health. She earned her PhD here at the University of Virginia in systems engineering in 2022, and her graduate work focused on applying supervised machine learning methods to novel challenges in mobile health, and is currently a data scientist at Stanson Health, where she uses large language models and traditional supervised models to optimize patient care. She's previously worked at Evolent Health, where she built supervised models for medical risk prediction. And outside of her work as a data scientist, she enjoys exploring the Charlottesville bookstore scene with her husband, Tyler, and spending time with her assistant, Benny the cat. And in continuing with our 2023-2024 Biomedical Data Science Seminar Series theme, Anna's lecture today is entitled Large Language Models for Healthcare, Where Are We Now and Where Are We Headed? This meteoric rise of large language models like ChatGPT and others has kickstarted this whole new era of computing wherein the answers to even the most obscure questions seem to be right at our fingertips. And advancements in LLMs have, in particular, opened up an entire new world of possibilities in the biomedical space. LLMs are now being used to answer complicated medical questions about patients' electronic health records, enabling clinicians and researchers to focus on identifying the best treatment paths for patients, etc. And in her lecture, Anna is going to skim the surface of how LLMs work and then discuss how they can be applied to biomedical and data science domains. As always, we are streaming this lecture live and for recording via YouTube. And so if you're watching us on YouTube, thank you so much for joining us. Also, our especially selected 2023-2024 Biomedical Data Science Innovation Lab participants and alumni are encouraged to submit any questions they have via the chat feature in their YouTube sessions. I will synthesize these questions and ask them on your behalf during the last 10 minutes or so of Anna's lecture. And with that, welcome, Anna. We are really looking forward to your presentation.
Thank you, Dr. Van Horn. Very happy to be here. So yes, as Dr. Van Horn said, I will be presenting as much as I know about LLMs, which is still certainly a very rapidly growing field within computing and at the intersection of biomedical data science and many, many other fields. So very exciting. This is the outline for my talk. We should take up most of the time, but let's see. I'll give you a brief introduction about what we do at Stanson Health, and then I'll go into some of the basics of LLMs, both from a high level and low level perspective, kind of showing you the meat and potatoes of what's behind these very exciting and mysterious black box machines and algorithms. And we'll, of course, discuss what that means for healthcare and some of the strengths and limitations that we've encountered in our work at Stanson. And then finally, talk about the future of LLMs in healthcare, which should lead to a productive discussion. So with that, briefly, I will just let you know. So what we do at Stanson is we use technology to drive positive healthcare outcomes. So for anybody who has had to deal with the US healthcare system, you would know that things called prior authorization, where often your doctor writes a prescription for something and the company providing services for your insurance needs to just double check that everything looks good. So to make sure that drugs don't conflict, that it's cost effective for everybody, things like that. And so we do what's called utilization management. We take that traditional model of putting all that work on nurse reviewers, which takes quite a long time and resources. We try to automate that with AI. And I want to emphasize we do that so that we can actually auto approve prior authorizations much more quickly. We don't deny. You may have seen different pieces of news lately that talk about the pitfalls of what happens when you just throw AI at this problem. But we're very, very careful to craft a fair outcome, and we only do auto approvals with AI. So this is supposed to be a much friendlier workflow for both providers and anybody else working in that space. And it's supposed to help patients not have to wait as long for decisions like that. So we make approximately 80% real-time medical necessity determinations, meaning you get an answer right then and there. So love what we do at Stanson. It's a very interesting space to work in, especially with the AI component. So with that, you may be asking, okay, I've heard about LLMs. What on earth are these and why are they so important right now? So if you're like me, you have seen just example after example, and you might be wondering, why are llamas important? Why are alpacas suddenly important? What on earth has ChatGPT done now? Suddenly, Google also has something, and I'm sure you have seen the hugging face icon everywhere. We're going to talk about that. At a fundamental level, LLMs, which we call large language models, are these very big deep learning models that are pre-trained on vast amounts of data. And you may say, great, what makes that different from a normal machine learning model? It's that the scale of these is kind of beyond comprehension in the billions and billions of parameters. And these algorithms that drive these models are so special because they can do tasks like summarization, translation, and prediction, as well as content generation. So this is a timeline of some of the innovation that has occurred even just up to March of last year. And so this is already outdated, as frequently happens in this research space. So you can see ChatGPT was certainly not the first large language model to come onto the scene, but it was one of the most talked about models and most popular. And so you can see this kicked off just this spree of innovation, especially in industry, but also in research hubs like Google. So you see Palm was one of the models that has been developed recently, something called Flan T5, Chinchilla, which was focused on efficiency, and of course, recently, more innovations from OpenAI with regard to ChatGPT. So just a ton here. Under the hood, so you may be wondering, okay, how do these work? So the architecture of LLMs is these are what we call transformer models, which are neural networks that learn context and meaning by tracking the relationships in sequential data, such as words in a sentence. And so you can see this example here from a very seminal paper in the field called Attention is All You Need. And it shows the relationships between words as an LLM sees them. So you can see, especially down towards the bottom here, not only can a word relate to itself, which for mathematics people would just be something like the identity property, you can see how words like my also relate to things that the first person is talking about, right? So in my opinion, all of those words are strongly connected to the word my. And so this is just an example of what it would look like to an LLM to map this out. And this type of model, transformer model, can be used to do seemingly simple things for a human in a very efficient way. It's certainly not so simple for a machine learning model, and I'll show you what I mean. So imagine a scenario where you want to predict the next word in a sentence. Now, this one's tricky. I went to the blank. There are many different things that you could guess based on this. Now, as a human, if I have context, let's say a friend is telling this to me, and I know that they were running errands and they had told me about this. Most likely, I would say, they probably went to the store. But for a machine learning model like an LLM, this is a lot trickier. These different components of this sentence have to be represented by probabilities and what we call weights. So, yes, the different coefficients, if you will, attached to the different pieces of information in that sentence. And so you can see here, it's this really complex structure that can be summarized to an encoder and a decoder, where on the left here, and the encoder takes the sentence and it assigns the different weights that it needs to actually represent it mathematically. And the decoder does something called masked multi-head attention. Now, I'm certainly not an expert in this, but what I can say at a high level is that attention goes back to that slide I showed you before. It's the mechanism that allows the LLM to focus on these different relationships and ultimately make an appropriate prediction for the next word. Now, I'm sure all of you are familiar with this example, so I threw it in here. It's quite funny. But on a serious note, you need to be able to learn from examples as a machine learning model. The neat thing about LLMs is that they can actually learn off the shelf. So they can learn about new tasks off the shelf with no examples whatsoever. So I could take ChatGPT and ask it to do something that it may not have trained on, like predict or let's say classify the type of tree that's out in my yard based on a picture. It may not have trained on that exact picture, but it has general knowledge of the world. However, you have to be careful because without examples, giving the LLM a novel task may not work as well, which is illustrated by this. I think a lot of people do think that AI is in this incredibly sophisticated state where it can make predictions left and right with no help. And that's not exactly true. If I were to ask a large language model to actually classify, or let me say a transformer model to classify a picture of a cat, it could very well call it a dog if it hasn't had enough training and experience of real world images. But if I give it an example, like several images of cats, or just one in this case, which we call one-shot learning, it may actually do better at classifying and discriminating between different pictures. So perhaps a more relevant example to what y'all do in biomedical research and what we do at Stanson with medical charts is learning with mathematical reasoning. And so we don't necessarily focus on this, but you can see an example of what happens when you walk the LLM through the logic required to solve a math problem. So this is what we call chain of thought prompting. So on the left, you can see you give it this math problem as an example, and you just give it the answer with no explanation. Unsurprisingly, it doesn't do too well at explaining its work like we are all required to do with a math problem, and it gives the wrong answer, and we don't know why. But on the right here, if you see how we walk the LLM through different steps of the process to get to the correct answer, it then can do the same thing in its output. So this is a variant of one-shot learning called chain of thought prompting. And it's very, very useful for things not just related to math, but also with interpreting text in general. And you can see the impact. So this is from a paper called Language Models Are Few-Shot Learners. You can see an example here of that compares model size and also whether you're using zero-shot or one-shot learning. You can see the larger the model size and the more examples you give it, even just with a few examples, the performance significantly increases. So this is a really interesting comparison. And if we move on to this, we'll see, again, this is only up to date to March 2023, but this should blow you away, basically. This shows, if you look all the way here on the left, you can see where GPT-1 started out with what is considered a very small model nowadays. So this is 117 million parameters, and it's considered this tiny speck in a sea of huge models today. And so you can see how these compare. BERT was another foundational model in this space. And again, it's this tiny speck. And so I encourage you, here's the link if you're interested. This graphic is really cool just to kind of see how far we've come with truly large language models. Now, one thing you can do with large language models is something called fine tuning. So these models can be fine tuned in the sense that you can take it, it's been pre-trained on a very large amount of data, but then you can also sort of retrain it. You can train it further to understand a novel task. So one example I'll give is what we do at Stanson. We use LLMs to understand medical charts. And you can imagine a generalized model like T5, or Flan T5, may not have trained explicitly on medical knowledge, and certainly not exclusively. And so we need to we need to train over time so that the LLM gets good at learning, well, what kinds of medical terminology words am I looking for? Which words are important and stand out for our prediction task? So the way this is done is you give it a set of labeled examples, much like you would in traditional supervised learning. But in this case, the model's weights get updated in order to make better predictions. Now, there's been several examples of innovation in fine tuning. This is where we get into a little more math than I would be good at explaining, but like I said, at an upper level, so we have these two things called LoRa and QLoRa, and this is if you're interested at working on some of these low-level problems. So LoRa reduces computational costs by actually freezing the parameters of the model, and then using decomposition matrices to cut down on the sheer number of trainable parameters needed. Now, like I said, I would not be good at explaining how this works in detail, but what the takeaway from this is that it saves time and money and compute. So it's very useful, especially if you're working with some of those larger models. Now, QLoRa is a variant of this that actually came out last year that gets down to the bit level of how we represent numbers. So if you recall, for those of you who took computing courses or who work in this space regularly, you have to represent numbers to a computer with different bits, and you have your sign bit indicating if it's positive or negative, etc. This is an example of an 8-bit binary number. And so you can imagine more bits, more compute needed, more space, more time, etc. With something like QLoRa, you can reduce how numbers are represented down to a tiny 4-bit space and still retain accuracy and performance. Now, you can see this in action by some of the experiments that one of my colleagues did and that I have done in the past on different medical tasks. So in this case, and these are renamed just for the sake of privacy for the tasks we are working with, but at a general level, we work with medical charts. And so for task 2, for example, the green color, that would be trying to get the LLM to detect language describing diabetes in a patient's medical chart. Similarly, task 3 pertains to depression language. And so you can see when you just throw an LLM out of the box at one of these problems, if you compare it to a baseline, which in this case was XGBoost, the performance may not be much better and may be significantly worse because the LLM has no idea what it's doing. But if you fine tune it, suddenly you can see performance compared to the baseline is the excitement. It's better. It's what everybody's been talking about how exciting these models are. And so this is a great example of why you might want to pay attention to things like fine tuning if you start working in this space. I'm going to pause here for a moment. All right. So if you're still watching and you've stuck with me, which I hope you are, this is the meat and potatoes of why you're here. So we've gotten this broad overview of LLMs and what they do. Now I'm going to describe the uses of LLMs in healthcare from a perspective of somebody who's been working directly with it. It's a really exciting time. So one thing we might want to understand better first, though, is what is the difference between these generalized LLMs and medical LLMs? You can imagine these are trained on different data sets. So, and they're designed differently fundamentally. So a model like ChatGPT is supposed to have very broad knowledge of the world so that it can answer a variety of questions from many different domains. You can ask it about politics, science, health, religion, we've seen this in all the funny examples that people send each other saying, look at what ChatGPT told me. This is just one example. And it can address both medical and non-medical tasks, as can many of these generalized LLMs. But as we talked about, it may not perform as well. And so medical LLMs are of particular interest to this community because it's this powerful variant that we would hope would perform better on medical image data sets, on things like exam questions, which we'll talk about later, and of course on patient charts. And so medical LLMs like MedPalm, for example, or MedAlpaca are designed to have medical knowledge fundamentally and to use that to drive decision making. So these models are pre-trained on biomedical data sets. So you may be familiar with Mimic, MedQA. These include things like clinical notes, lab values, images, things that ChatGPT most likely did not focus on. And as a result, these models in general are likely to perform better on medical tasks, such as answering complex questions about a patient's chart. And so that's the first example I'm going to give you. We at Stanson use LLMs to extract info from medical records. This, by the name, is called extractive question answering, and it helps us quickly get information about a patient's medical history. So for those of you on the medical side, instead of more of the technology side, which is probably a lot of this audience, you'll notice here, this patient is probably at risk of a few things. And so the first step to understanding this patient might be to say, well, we've got to check the patient's A1C pertaining to blood sugar. And so we can ask that and get a very straightforward answer. This is partially, and so this is wrong. This is a typo on my part, but it's 6.2. So this would be an indication of information being clearly there in the record and easily extracted. You can imagine this is a lot simpler than doing something like programming out exactly how to extract number from this part of chart and move to this data frame, etc. A lot less tedious and a lot more user-friendly to just ask in natural language, give me this measurement. So that's one example. Now, the next step to that, if you will, is to identify patient risks. This is a little more tricky because this is called generative question answering. It's used where the information you're looking for may not be explicitly stated in the patient's medical record, but we need answers to help understand what conditions the patient might have. And so the LLM kind of has to learn through all of its weight updates, the encoder-decoder structure. It has to learn how to understand, oh, these numbers in together might mean the patient is at risk of diabetes or prediabetes and hypertension. And so that's tricky. You certainly have to have a lot of examples to get it to start to understand what it's looking for. And I think the third, so this is way out of my domain, but it's certainly a cool idea for future work on our end, is interpreting medical images. So MedPalm has been kind of famous for this, and it's certainly not the only one, but you can see an example here of interpreting a patient's MRI of their lungs and understanding if there's something like a collapsed lung or internal bleeding, something like that. And again, forgive me, I'm not a medical expert. But this shows how quickly you could get answers in a setting like a trauma ER, for example, where interpreting images quickly can mean the difference between the patient coding and not coding. It's very important. And so a lot of you may be asking, okay, but what's the actual proven performance on this? I'll give you an example. So this one, I think this is the paper that scared everybody because this is the one that showed tools or models like MedPalm can actually answer questions from the US medical licensing exam with such accuracy that it could pass the exam. Now, nobody is saying this LLM is a doctor by any means. That opens up a whole can of worms. But what this does show is that it can answer these questions with pretty high accuracy. And not only that, but if you look at this chart on the right, this shows that oftentimes the LLM's answer can actually demonstrate decent reading comprehension, good knowledge recall, high reasoning. So things that we would not expect from a machine learning model. And oftentimes, forgive me to the physicians who participated in this, but oftentimes the LLM's responses were preferable according to independent raters. So I think all these examples serve as just this comprehensive look at what LLMs can do in a rapidly changing field. However, we should talk about the strengths and limitations. So obviously, the strengths are that LLMs are efficient at synthesizing really complex multimodal clinical data sources. So as I showed you, medical charts, lab values, images, things that a doctor needs to be able to synthesize quickly to make decisions for a patient. The LLM can help speed this up. LLMs can also answer these complex questions with almost no examples, which is really exciting. These are also easy to use in a clinical setting when set up right. So the doctor can use natural language to actually request assistance in interpreting medical results. This could be used by nurses during intake. This has many, many, many possibilities. And it can also solve a variety of tasks. So all of these models can solve a variety of tasks, even if they aren't medical specific models. However, as with any great pioneering technology, there's going to be some limitations. The first of these, I love giving this example, is hallucinations, which is essentially the model is confidently wrong. And this can mean a number of things. It might be that the model makes up an answer because it has no idea what to do. It may give a complete nonsense answer, or it may even conflict itself. And so I love this example because this happened to me. I was working with a data set where I thought, okay, I'm going to mix in these different types of questions. Some of them required yes, no answers, and others required more complex things like a list of conditions. And so that's one of the things I asked. I said, LLM, please list all the conditions that patient Joe Smith has been diagnosed with. It says, yes. That's all it said is, yep. Didn't know what to do because it had this mixed training set and it hadn't mastered the task yet. Another one of the large limitations, of course, is cost. You'll notice a lot of the people and organizations that have been able to make these models bigger, better, and faster have a ton of money behind them. This is a little disappointing because not every institution like UVA has the benefits of something like Ravana, where we do have access to GPUs and sufficient compute. A lot of times you need millions to billions of dollars just to train and maintain these models. You also need sufficient compute capacity, not only to do the initial fine tuning, but also just to continue running these models in production long term. And this is a big barrier to entry for a lot of people and a lot of companies. In case you're curious, you can actually find estimates of how much these models took to actually train. The cost estimate of Palm, Google's model, which has been adapted to variants like MedPalm, is estimated to have cost at least $9 million just to pre-train. I don't have that kind of money, and I don't know many people who do. And one big limitation now, I understand, Dr. Van Horn, you said you all have talked about bioethics in past series for this lecture series, and I would encourage you, if you're thinking about working in this space, to revisit that. So one of my colleagues, actually almost exclusively right now, is working to ensure that any models we build, especially LLMs, avoid bias. Now, bias can mean a number of things in a machine learning context. What I'm talking about here is more on the social dynamics definition of bias. So, So basically, a model trained on biased data may perpetuate stereotypes, which can lead to very real and negative implications for patients. Things like misdiagnoses, missed or misdiagnoses, so both of those, worse patient outcomes over time, just a whole host of issues. And a lot of times these are biases focused on racial and socioeconomic lines. So there was a recent Nature Digital Medicine article that actually showed LLMs may falsely claim that Black patients have a higher pain tolerance than white patients, which is false and could be devastating if implemented in a production setting. So again, I would encourage you, if you're thinking about going into this, please take time to think about what your training set looks like and how you're planning to apply this model in an ethical way. So you may be asking, what's next? And I'm keeping an eye on time. Looks like I might be a little speedy today, so we can take a little bit of time on this slide. So the future of LLMs it's hard to ask and get a straight answer, but I would say in healthcare, these are the things that I'm kind of anticipating in the next year or two. I think we're going to see continued just rapid development of new solutions, especially for patient care. So I believe Epic, which manages many electronic health records for a ton of the country, believe they're partnering with Microsoft to do some kind of a trial run with using LLMs integrated into their patient charts. So very exciting, especially if it speeds up workflow for clinicians and for clinical care providers in general. We're also going to see this probably a lot of adaptation of open source LLMs to the medical domain. This has happened already. So Alpaca, if I recall, forgive me, but that was a Stanford model that was adapted to something called MedAlpaca, which was focused much more on the medical domain. And so people like open source because not the community can contribute to it, and it lowers the barrier to entry. You aren't paying a large corporation to actually use these models. So, hooray, open source. There's also going to be, of course, on that note, this tug of war between open source and what I would call pay-to-play LLMs. I think we're going to see a lot more tension between independent research groups working on these types of challenges, companies that are trying to monetize things maybe on a smaller scale, and then very large companies that are already doing this. So that will certainly be interesting. And of course, there's going to be quite a lot of debate on how these models and the ETL, what we would call extract, transform, load, how you're getting the data from one place to another securely, because you can't just upload a patient's medical records to an OpenAI database. There are so many protections that need to happen. I anticipate on a federal level, we will likely see guidelines at some point in the future as to how this should be governed. At least I would hope so. And so that's most of what I have, but I will say if you're curious about how you can start working with LLMs, these are just some general resources. These are very, very high level resources. I don't know. These aren't specific blog posts or anything like that, but I would encourage you to look at them, especially if you're new to this. So Hugging Face is basically the hub for transformer models everywhere. You can find pretty much anything you want on there, and it gives great code examples and walkthroughs and deep explanations of how these models work. And you don't have to be an experienced coder to use it. You might want to be familiar with Python or get to that point, but it's a very user-friendly website. Just a lot of documentation. If you're a nerd academic like me, you will probably be following arXiv 24/7 because honestly, this is where most papers are coming out. And it seems like there's a new one every day or every few days. This is the best place, one of the best places you can find new research with regard to LLM implementation, efficiency, anything in that realm. And then interestingly, this will show my age, LinkedIn has been really useful. So I often see when I do go to LinkedIn, I see independent scientists and researchers and company representatives all talking about their benchmarking experiments that they've done or recent papers that were released. So LinkedIn is a really good knowledge dissemination hub for this. And then finally, one course I found really helpful when I started to work with this is called Generative AI with Large Language Models. And I believe that's taught by Andrew Ng. I would have to double check, but it was really, really good, quite short, beginner friendly. And it gave you just a basic breakdown of what these models do. So I highly encourage you to take a look at it. And that's not a business plug, that's just a plug about how this helped me quite a lot. And so with that, I am a bit speedy today, so we should have plenty of time for Q&A. And obviously, Dr. Van Horn, please pass around my email to anybody who needs it. And yeah, I'm open to any questions you have.
Fantastic, Anna. Thank you so much for that. I think, when you showed the USMLE graph, everybody kind of was reminded that, our radiologist friends might be in a little bit of trouble, especially if the LLMs, the responses are preferred. The role of radiologists might need to be or might be changing, which is really interesting. But I keep seeing things like that where large language models are being asked to do the job of that maybe somebody who's been doing this kind of particular task before, and there's a whole career path about it, and yet LLMs have sort of now being able to do that and perform as well, if not better, in some instances. Are there any other examples of where you're seeing that kind of thing, especially as it relates to healthcare?
Yeah, so I will say, especially for anybody who's just cringing in the audience and going, oh my gosh, my job is being threatened. I will say I have not encountered an example in my job where we could only use these models to make decisions, except for that auto approval piece I talked about. But that is to the benefit of the patient always. It's just a quick approval and off you go. I think for anything that's not an easy predictive problem, if you will, you're still going to need human intervention. So we still need radiologists to help interpret these images because these models aren't always right. It's no different than a team of doctors getting a second opinion or third opinion from each other for a complex medical case. That being said, so yeah, examples of where this can be used in an automated way. Auto approvals is one. Outside of healthcare, chatbot responses and customer service, I've seen a lot of. I'm sure I've used one at some point where it makes it easier so that customer service representatives don't have to go back and forth on some of these simpler cases, like I have an Amazon return to do. I think that's the biggest one I can think of right now. So I could see this. I see these models directly affecting commerce right now in an automated way. Healthcare is still a little bit far off from that.
I'm curious on maybe you can expound on this a little bit as there's the nervousness about turning over the decision making to the machines, versus having these serve as a tool or even a colleague. You mentioned like getting second and third opinions. As a tool or a colleague in some of the decision making processes in biomedicine, and how those can kind of help. You can be a little bit of a give and take to kind of inform clinical decision making and research decision making. Maybe you found a little bit more on that relationship that we seem to be building.
Yes, it's delicate, right? And it can be fraught with concern over whether AI is giving an accurate representation of the patient. So I think there's so much we could talk about there. I think one of the big things is that, yeah, I think clinical care providers are learning that AI can be useful. And well, I don't want to insult anybody. Many already use AI in their practices. Some are more hesitant for good reason. I think what that relationship is going to look like moving forward is going to depend on the ethical considerations and safeguards put in place by model designers and tech evangelists, if you will. Clinicians are going to need to be confident that people like me are building in extra safeguards to say, yes, we're confident that the model's answer that this patient is at risk of diabetes is true. And that's actually a good example. So it is, they talk about the risk of different types of errors you can make in machine learning. So you say something is true and it's false, or you predict something is false and it's true. It is much better in this case, and I think we could trust LLM predictions to say this patient is at risk of X. Because the worst thing that happens is the doctor takes a second look at the chart and says, no, but I've paid a little extra attention to this patient and maybe I catch something else. Alternatively, if you trust predictions that say, no, they're not at risk for anything or this condition, it creates some doubt because they're not perfect machines. And so I think ultimately, clinicians are still the authority here and will need to be for quite a long time. The LLM is a tool, it's not a clinician.
What are some of the implications you mentioned in your presentation about some of the how some of these things work and how they perform when they're zero shot or one shot or a few shots and what are some of the limitations about the number of shots that one can take on medical records because there's often medical records are they're just sort of kind of a mess really sometimes there's lots of poor structure. There's some sort of like lots of free form text. So there's lots of doctor lingo and shorthand for that may mean something to them, but may, to even to a large language model, unless it's trained on it, it might not understand that. What are some of the limitations and challenges that exist there?
Yes, actually, you brought up some great examples that we've encountered firsthand. So let me think about how to describe these. The first one that will be most familiar to people already working in this space is the length of the context window. And for those of us who don't work 24/7 with LLMs, what that means in plain English is how much stuff you can send to it before it goes, I have no idea what to do because it's reached its limit in terms of size. Now, with text in NLP, we break pieces of text up into tokens, right? And so the smaller models might say, I have a token limit of 512 tokens, which is very short. The one challenge or consideration that you have to be careful of is if you have this really large medical chart and you want to include things from the past in the patient's chart, not just the notes from today, you're going to have to be very selective with what you send in. So some of the techniques we use is we have to we use statistical calculations to say, okay, which piece of text is the most important? Which ones do we want to include in what we send off for prediction? And we don't send all of it. In the future or now, that may actually be changing because context windows are getting so much larger. Then the consideration becomes efficiency and time, right? You can send a whole medical chart, but it's going to take a long time to process. And Dr. Van Horn, as you pointed out, there's going to be this challenge of messy text, right? Nobody ever gets clean text when they parse it from a medical record. Yes. And so I know at Stanson, we use techniques to tidy that text up before we actually send it off. It's part of our pre-processing for many things we do. So if you're thinking about testing out interpretation of clinical notes or whatnot, you're going to need a good data processor for that. And that's likely going to be a human plus a machine who knows what they're doing.
What sort of I'm not even sure if I know quite how to ask this, but at the moment you go to a website like ChatGPT or to your favorite large language model, website, you input some text into a text box and hit return, and it asks it to do something, and then it returns to you text or however you're interacting with it. But on the other hand, like you said, with certain medical records, you can't do that. There's identifying information in there. Sending it out into the wild to be processed at Google or whatever is probably fraught. Are there any attempts to uh, say take a large language model and burn it into hardware and then sell the hardware to hospitals so that they can use it within their firewalls and all that stuff so that patient protections are more assured? Does that make sense?
It does, yeah, and you're close. It's this is a little outside of my domain, but this is more in the privacy and security domain. But as I understand it, yes, the goal for healthcare systems is going to be, in the current state of things, they would probably license a certain version. So UVA Health might say, we want to license Flan T5 extra large, or more likely something like MedPalm. And so they'll probably pay a subscription service or do something like that. I hope not, but that's probably the way we're headed. And in turn, most likely somebody from Google or an AI expert will come in and get this variant of the model set up for them in a custom way so that yes, it lives within the walls, the figurative security walls of only that institution, and you aren't sending information out willy-nilly, if you will. So I think that will likely be something we see a lot of in the future. And what that opens up is a lot of opportunities for new jobs, quite honestly, not only for AI experts, but also for physician consultants who need to come in and say, yes, this is okay. No, this isn't. Which components, what is the minimum amount of information about our patients that we can run through this model, even though we've kind of kept it within our walled garden.
Can you say anything about uh, query engineering? Is that the right term? Basically, there are ways to ask these large language models things. There are multiple ways to do it. And there's some ways that are better than others. And that engineering thing, it's turning out to be a special skill set amongst, yeah, again, you talked about different jobs, and that this is now something that apparently one can do as a potential career. Could you say a little bit more about that?
Yes, that should have been in my slides actually, but I can certainly speak to it. So prompt engineering or query engineering, I think both of those are valid. It is, yeah, it's a rapidly growing part of the field because it turns out if you're an engineer that also knows how to use natural language appropriately, people want to hire you. Now, what that means is you're probably, so let's say you're thinking, oh, I'm interested in being a prompt engineer. You have to, it's more of an art sometimes. You have to deeply know the data set you're working with and the types of questions you want to ask. So the simple example is what I talked about before. Do you want to ask a yes no question? Because actually formulating LLM outputs to match yes or no as a prediction can even be tricky. But do I want to ask a yes no question? Do I want a list of conditions? You need to know fundamentally and be confident in what the end goal is. You also need to know some basics, yeah, just like formatting. Like, is it better to tell the LLM, I'm going to ask you a question, here's the context, or is it better to just straight up ask, LLM, give me an answer to XYZ? So again, it's kind of this art of playing with templates for human speech and how we would ask a machine. And sometimes real little things can trip you up, like you included a weird character in your context and suddenly it just doesn't like anything. Those kinds of things are tricks you kind of pick up as you learn this.
You had a graphic in there that I think you got from, I can't remember where you found it. It was that lifearchitects.ai/models graphic that shows all these different large language models and their relative size with respect to each other. And of course, this is the wavefront of these is moving like crazy. So the large language models that, today are so big in 18 months are going to be considered cute by, the size that they're growing. One question I had about that, though, is that there's multiple different models. Are there any attempts to create kind of some meta models that like go across the different large language models? So it's not just one large language model one is drawing from, but they somehow are aware of each other and can, pick up where another one might not be as dense or as rich.
Ooh, okay. That's really an interesting idea. And I
Okay, forget I
have
mentioned it.
not.
I'm going to go open a business.
Yeah, no, I haven't seen that. I think the challenge, right, is that they would all have to be within the same suite of models or company.
Okay.
So Google could do that because they have different types of LLMs they've crafted for different purposes. That would be harder to do if you were trying to, probably impossible to do if you were trying to make a Google model talk to a Meta model, for example. I think what is becoming popular, and this is where engineers still come in, is let's say you don't want to be a prompt engineer and you're not a clinician. You like to program, kind of like me. Um, you could be the person who assists in what's called retrieval augmented generation. So, certain types of complex queries, particularly in math, will often need to outsource part of the question to a traditional program. So, it's hard to describe, but basically, you could be the programmer writing little snippets of Python code that the LLM will refer to when it's doing things like complex math or struggling with the context of what patient or what clinician shorthand means in the context of a medical record. So that is kind of what I'm seeing now as the innovation piece for making LLMs talk to other systems. They aren't standalone anymore. They're using other code alongside of them.
Yeah, I could see that being very powerful in that you could have these very focused um, uh, LLMs that are very domain specific. You know, you're going to have one that's kind of the general one, right? But then you have these others which are much more of a deep dive into whatever that particular topic area is. So it doesn't have to be in the larger language model, but elements of it could be. But then you'd have these hooks that would go into the deeper one to pull out more information. Of course, from the user's perspective, they don't see any of this. It just, happens. But from a technological and back end point of view, that might be an efficient way to do it so that you're not having to carry around extra language that you may not use if you're not a radiologist, for example. You're somebody else, but somebody who's a radiologist and want to ask a question, the large language model would know, well, I don't have that on hand, but I know where to go to find it. And they could draw from another model. Um, one of the things which is kind of interesting about our biomedical data science innovation lab and our seminar series is we get to get opinion and input from people who are from not only from academia, but from the government, and in your case, from private healthcare organizations. And I'm kind of curious, from your perspective, as having got your PhD just a couple of years ago, and you're out in the world now. What are some comparisons and contrasts that you're seeing from the academic world and what people are considering with large language models in academia versus what are some of the things that are being seen as important in organizations like yours?
Yeah, great question. So I can tell you the big overlap is efficiency matters. Efficiency and accuracy matter in both academic research on LLMs and in what we do. We could get our hands on the largest model ever that makes the best predictions in the world, but as my boss reminded me, it may not do what we need it to do because the latency could be too big, or it could just take too long to make a prediction. So I really appreciate the studies that have come out recently. So I think chinchilla was the big one I remember, but there's so many showing the feasibility of LLMs as they come out of the box, the importance of condensing some of the weights and the bits and the bytes and things like that to make it smaller and more efficient. I really appreciate that kind of research coming out. I think the things that have been important to us that I never would have thought of in academia are much more, they happen in our meetings with our clinical product team. So we consult with them so much. So let me back up. In academia, I had lots of opportunities to interact with clinicians in my last year of work, and it was wonderful. But it was a different type of work. I was much more focused on writing my thesis, getting the experiment executed, et cetera. But now I have to actually be good at holding conversations with clinical product and to say, are we doing this right? Did we implement this correctly? Did I actually get the right abbreviation for what this means? And so I think that's an example of things that I wish academia would do more of is consult with clinical experts in designing these systems. I think the big projects and papers do a good job of that, but anybody who's getting into this research, you have to form those connections with medical teams.
I'm glad to hear you say that because our theme this year for our Biomedical Data Science Innovation Lab is building the partnerships for generative AI training in biomedical and clinical research, with the theme being that the people who are developing these tools and developing these large language models and cultivating them and optimizing their use, being able to have partnerships who are working, at, patient facing, or who are doing research where these things are, they want to use them. And then also, how do we train people to use these? And this is, I guess, the question I wanted to ask you next is, what are some things that we need to think about as, you're a fairly recent PhD from just a few years ago, but like as somebody who is learning about these, what are some of the things that people might need to know about these in order to use them effectively? And how that's not just the end user, but also the developers. What do they need to know about how people are going to use these things? And what do they need to know in order to make it so that it's transparent, that biases are removed as much as possible? What do they need to know as they're developing these things?
Yeah, I think it's hard to know everything you need to know until you've had the experience, which you have to have experience to get experience. I know that's the joke, but in all seriousness, I think there's a couple facets of this. I think one, you have to get comfortable with coding if you're not, and be confident that you can learn that skill if you're new to it. So uh, the the people that I work with are from a broad range of backgrounds, and some of my colleagues are huge Python gurus, like, and I'm definitely not. Others of us are a little bit more in the middle between human-centered computing and pure computing, if you will. So I think number one, get comfortable with programming and making mistakes in your code, and learning how to fix it. That's on a very practical level. Do trainings, do see if you can learn how to work with tools like Amazon SageMaker, where you can get models up and running and test them. So that's one thing, and Coursera is great for that. Another thing, on the other questions you asked about, what do we need to know to be prepared for avoiding bias and to making sure that it works well. I, get comfortable having conversations with your team members, with clinicians, and I think staying on top of the literature is really important. I say that because I'm an academic, but don't be afraid to dig into these enormous, kind of overwhelming papers that are coming out, and try to pick out the pieces that you think are impactful in your line of work, and get good at it. If the important thing to you is accuracy of the model, try to build an accurate model. I think it's a lot of practice makes perfect, and keeping, on top of what's going on in the world.
Do you have any parting thoughts for us about large language models? And you mentioned kind of, you said where they're going to go. Where will we be? Again, I was just thinking about this the other day. It was what, like 18 months ago, we started to first hear about ChatGPT, and now it's like, the overwhelmed us in a degree. What do you see us in, say, another months, and where might we be in a couple of years with these?
Oh, um, I think I'm assuming a lot of positive things will happen. I'm trying to be positive here. I see a lot of companies really, like Stanson, for example, really eager to get these out into their products because we know it's going to positively impact so many people. And so I anticipate, I think there's going to be a lot more healthcare startups popping up that try to use these. I think there's also going to be a lot of counterbalance to that. I don't know at a federal level, but just in the community, about how do we develop safe practices for these. If I told you where we'd be in a year, my answer is I don't know, because this changes so quickly. But I'm excited to find out.
I think I am too, Anna. And I want to thank you again for sharing your thoughts with us, some of the implications of large language models, how they're being utilized in healthcare. This is a fantastic talk and a great conversation at the end. So thank you so much. Thank you,
Thank you.
everybody who is watching us today and in the future. And everyone have a wonderful weekend, and we'll see you next week. Thank you again, Anna.